In the course of physics of solar energy conversion, we analyze the harvesting of solar photons and how they create the photocurrent. We have seen the ideal model for a solar cell in which there is generation and recombination, and the external light creates a photocurrent or short circuit current, that is this term, and we want to quantify this term. This is essential for the production of power of the solar cell. The larger the photocurrent will increase the power that comes out of the solar cell. So we start with the simple ideal model in which the Fermi levels are flat and we have light generation, recombination, and extraction. And we use a model for a semiconductor that is a step of the bandgap from 0 to 1 in the absorptivity. Here we could already calculate the radiative VOC, and now we want to calculate the photocurrent that is coming from this type of solar cell. The simplest way is to treat the incoming solar energy radiation as a black body radiation. This approximates the solar radiation with an analytical expression that we have discussed previously. So this is going to impact in the semiconductor, and then the solar energy utilized are these photons because they are absorbed by the semiconductor, while the semiconductor is transparent to those that have less energy than the bandgap. If every photon that comes is converted into an electron extracted, this is a quantum efficiency of 1, and then simply we integrate the given spectrum from the energy of the gap upwards, and then we can even get an analytical expression for this current. It means that this is the number of photons coming from the black body spectrum representing the sunlight. It means that we are going to take only those above this tail, above the bandgap. This is the one that are going to be converted to current. And this is the fraction of energy that is utilized, because each photon is converted into one carrier, so that this is decreasing when the bandgap increases. So a smaller bandgap, of course, will give a larger photocurrent. Here is the direct integration of the blackbody spectrum at 5,800 Kelvin, and then we can see that at very low bandgap we can obtain the whole solar spectrum corresponds to 70 milliamps per centimeter square approximately. If we go to a bandgap of 1 electron volt here, this is about 40 milliamps per centimeter square. If we are at 2 electron volts, then we can collect only 15 milliamps per centimeter square. Now, this simple picture needs to be improved in 2 ways. One is that we need to use the real solar spectrum coming to the Earth, the standard spectrum, to predict the power conversion efficiency and the photocurrent. And the second is that not all the generated charges are extracted equally. So there are questions of how intense is the absorption at each energy, or the transport of charges. There are different aspects, and all these are contained in the photovoltaic external quantum efficiency that indicates in the end the current related to a part of the spectrum. So that when we have the sunlight spectrum coming in and we multiply by the external quantum efficiency, then we can obtain the photocurrent that is collected by integrating over all the energies. So in this case, we can see that the green element has a higher absorption than the red element. Consequently, it will give a higher photocurrent. This is the external quantum efficiency of different photovoltaic technologies. The final wavelength depends essentially on the bandgap of the given technology, but then it will depend also on the absorption coefficient, etc. So by integrating the solar spectrum, we can obtain an ideal limit of the photocurrent, so that at 1 volt it is about 47 milliamps per centimeter square, and then we can see how the different technologies realize this limit, so that some of them, like crystalline silicon or gallium arsenide or the perovskite, go very close, so that they harvest very well the solar spectrum. We have seen that the power conversion efficiency has 3 elements: the photocurrent, the fill factor, the VOC. When we increase the bandgap, we have less current, but the VOC is larger, so that the carriers are extracted at higher energy. So in the end, we will find a compromise between low bandgap that gives higher current and large bandgap that gives higher voltage. So here in the middle, we will obtain the optimal efficiency by the tile balance arguments. This will be the object of another chapter.